Good morning everyone. Coming to third unit, that is combinational logic design. That is here you can see the functionality of almost all combinational circuits, and also you can learn how to write VHDL program for each and every combinational circuit. So coming to first of all a decoder. Let us take a combinational circuit decoder. So what is decoder? You can define the decoder as multi-input and multi-output logic circuit, and it is used to convert a coded input into a coded output. That is, and you can express the size of the decoder is n by 2 power n, where n represents the number of input bits at the input code word, and 2 power n represents the number of output bits at the output code word. In the decoder also you can get one-to-one mapping, that is for every input combination. For every input combination, only one output is become active, whereas others are inactive mode. Okay, so that is the about the decoder. Then coming to symbol of decoder is, this is the symbol for the decoder, represented with the size, that is n by 2 power n, where n is the number of bits in the input code word and 2 power n is number of bits in the output code word. Also it has some enable inputs. Okay, so you know enable inputs acts as a control input. Suppose if you take a 2 to 4 decoder, what does it mean? It has 2 inputs and 4 outputs. Simply you can say the decoder, you can draw the symbol for this 2 to 4 decoder like this. It has 2 inputs, say A, B, 4 outputs, say Y0, Y1, Y2, Y3. Let us see the truth table for the 2 to 4 decoder based on the action of it. What is the action? For every input combination, one of the output become active. One of the output become active. Okay. So let us draw a truth table with two inputs. Initially. That means without enable input. Here only data inputs I am showing. So the inputs are A, B. The inputs are A, B, and 4 outputs Y0, Y1, Y2, Y3. Under 2 input variables, how many possibilities in binary notation? 4 possibilities. Those are 0, 0, 0, 1, 1, 0, 1, 1, right? So for 0, 0, for every combination, that is the functionality of decoder. For every combination of input, only one output become active. Suppose for 0, 0, so Y0 is in active, only Y0 in active, whereas other outputs are in inactive mode, right? Similarly, for 0, 1, only Y1 is in active, others are in inactive. Like that, for other two combinations also, you can develop truth table of 2 to 4 decoder in this way. Okay, for every input combination, only one output is in active. Okay. So this is a truth table of 2 to 4 decoder without enable input. Suppose if you consider enable input also, when the enable is 1, you can observe the decoder action. The decoder action, when the enable input is 1, totally the logic circuit is in active mode, it shows the decoder functionality. Okay. Otherwise means when the enable is 0. When the enable is 0, whatever input combination you applied, that is A, B values either zeros or ones, the output is, since the logic circuit is in inactive, all outputs at logic 0. Okay, so like that you can develop the truth table for the decoder. And now the realization of 2 to 4 decoder using gates. So before going to realize, it is better to write Boolean equation for each and every output. Okay. So let us see what is the Boolean equation for Y0. Since Y0 is 1, when inputs are A equal to 0, B equal to 0. So therefore for Y0 you can write equation Y0 equal to A bar, B bar. Okay. Similarly, y1 a bar b, y2 a b bar, y3 with reference to y3 it is ab just. It is just ab. So like that you can write Boolean equation. So once Boolean equations are available, you can easily realize the logic diagram. So since all the output equations are represents the product terms, okay, so that's why the preferable gates are AND gates. Preferable gates are the AND gates. Okay, so let us see how to draw logic diagram for this. First of all, represent all inputs. All input means data inputs. The data inputs in true and complement form. Okay, first of all, you just draw data inputs in true and complement form. Okay, this is the with reference to a true line. So with reference to a true line, and whereas this one is complement line. Similarly, with reference to b, this is the true line and this is the complement line. Now another input also there, that is the enable input. The enable input, but enable input is only true I am taking. Why? Because when the enable is true, decoder functionality you can observe, and the enable is 0, all the outputs are at the zeros. Okay, then the preferable gates I said already, AND gates. Since here 3 inputs are there, so 2 data inputs, 1 enable input, that's why 3 input, and the size of the AND gate is 3 input, that is 3 input AND gate you need to take. So for y0, the connection is like this. For y0 AND gate, since y0 equation is a bar b bar, y0 equation is a bar b bar, therefore the inputs of this AND gate is a bar line, a bar input, b bar input, and enable input. Right? Similarly, for y1 a bar b, for y1 a bar b. Okay, so for y2 a b bar, a input, b bar input, like that. For last one, for y3 a input, b input. Okay, of course enable input already there. So in terms of data inputs, we have written the expression Boolean equation. Okay, this is the realization of 224 decoder using AND gates. Okay, but coming to CMOS logic, the realization of NAND gate takes less number of transistors compared to AND gate. Okay, so initially NAND gate was developed. After that, the combination of NAND and inverter gives the AND gate, right? So the number of transistors for AND gate are more compared to NAND gate. So it is better to realize using NAND gate instead of the AND gates. Okay, so for realizing the logic diagram for 224 decoder using NAND gates, the truth table slightly modified like this. Okay, here the modification is all output signal line values. You just invert. That means instead of 0 you place 1, and instead of 1 you place 0. Okay, then whereas with reference to enable, so when the enable is 0, show the decoder action. It shows the decoder action. When the enable is 1, the logic diagram is in inactive. That means whatever AB values, therefore all outputs at the ones. Okay, so this is the truth table for the 224 decoder if you want to realize using NAND gates. Okay, so the corresponding Boolean equations for y0, similarly whatever Boolean equation we developed for in case of NAND, and here also same. So y0 equal to, y0 is with reference to y0 a bar b bar, with reference to y1 a bar b, y2 a b bar, y3 a b. Okay, so this is the way how to write the Boolean equations. Then construction is similar to in the process how you connected logic diagram in case of AND gate. Similarly in the NAND gate also, first of all represent all the data inputs both in true and complement form, and enable in the complement form. Enable is only in complement form. Means when the enable is 0, it shows the decoder functionality, otherwise it can't. Okay, then first of all let us see how to realize why not. Okay, why not is for through NAND gate. Okay, one input is A bar, another input is B bar, and third one is enable bar. Okay, similarly other outputs also you can realize. Okay, this in this way the realization of 2 to 4 decoder using NAND gates can be done. Okay, clear? So you practice it. If you have any doubts, then take the clarification. Okay, then this is the actually up to this whatever we have seen how to develop the logic diagram for the decoder, all you already studied in STLD. Okay, coming to our subject, that is DSD. Here we have IC version. For each and every combinational circuit there is a IC. What is its number, what is the pin diagram of it, what is its internal logic diagram, and with reference to pin diagram how to develop the truth table, then how to write the VHDL program, that you have to learn here. Okay, okay, now coming to IC version, one IC is 74139. It is a dual 2 to 4 decoder. 2 to 4 decoder, what does it mean? This IC consists two to 4 decoders. It has two 2 to 4 decoders. Okay, so let us see the pin diagram of this IC 74139. This is the 74139 IC pin diagram. So here the upper part represents the one decoder, 2 to 4 decoder. The lower part also represents one 2 to 4 decoder. 1A, 1B, 2A, 2B are the data inputs for the 2 to 4 decoders, and 1G, 2G are the enable inputs. 1G, 2G are the enable inputs, whereas 1Y0, 1Y1, 1Y2, 1Y3, these are the outputs with reference to first decoder, whereas 2Y0, 2Y1, 2Y2, 2Y3 are the outputs of the second 2 to 4 decoder. Okay, and if you observe, some of the signal lines consist a bubble on it, and some other cases it is absent. Okay, so what does it means bubble represents the active low. That particular line is active low. Okay, that is, it needs, for active it needs low input, that is 0 input. For 0 input, that particular signal line become active. Okay, suppose 1Y0 is in active when its output is 0. When the output is 0 on this line, that is Y0 is in active. Okay, so similarly in the second decoder also. Okay, and if you see the logic diagram of this, so how to construct the logic diagram or how to remember logic diagram means, previously already we have seen how to draw a logic diagram for 2 to 4 decoder using NAND gates. In similar way, here also you can draw it. So see, these are the NAND gates, 4 NAND gates we require. Sorry, 4 NAND gates with reference to first 2 to 4 decoder. Okay, so this is the enable input. Yes, enable input through a NOT gate, bubbled inverter. It is bubbled inverter. Okay, like this. And whereas all data inputs also we can take both in true and complement form. This is the true line, this is the true line, whereas this is the complement line. True line, complement line. Similarly for data input 1B, complement line, true line. Okay, and already you know the equations for each and every output, how the equation can be derived. I shown in previous slides. Okay, so that you can easily draw it, right? Similarly, this is the logic diagram for second part, that is second 2 to 4 decoders. Okay, it's not such a difficulty. In previous slides, if you observe clearly how to draw 2 to 4 decoder logic diagram, here also you can easily draw. Okay, then another IC is Okay, this is the truth table for this. This is the truth table. Okay, 1, 2 to 4 decoder. Already in previous lectures we have seen AB are the data inputs. G is the enable input. G is the enable input. Underscore L extension represents enable input is active low. Enable input is active low. Okay. Similarly, all outputs are active low outputs, right? Because the bubble is presented in each and every output. That's why they are active low outputs. Means if 0 is there, that output is in active. If 1 is there, that is in inactive case. Okay. So like that, if you see, if the enable data is 1, if the enable, because it is active low, suppose if on the signal line the value is 1, the total logic diagram is in inactive. Whatever AB values, all the outputs are at inactive. Inactive means under logic low case, you have to write the value 1. Okay. Suppose if the enable is 0, that is this particular enable input is active, totally the logic diagram is inactive. It shows the decoder functionality. What is the decoder functionality? For every input combination, one of the output is in active. So here for 0, 0, why not is active? Why not is active means because it is at active low, you have to place 0. Okay. If inactive means you have to place 1 like this. Okay, like that the truth table you can develop. Then coming to another important, very important decoder is 3 to 8 decoder. This is widely used IC, that is 74138. IC 74138 is a 3 to 8 decoder. It means it has 3 inputs and 8 outputs. Okay. 3 data inputs are ABC. 8 outputs are Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7. All the output lines are at active low outputs, whereas data inputs ABC are active high. In addition to this data inputs and outputs, 3 enable inputs also it has, named as G1, G2A, G2B. But G1 is active high data, enable input, whereas G2A, G2B are active low enable inputs. Okay. Clear? This is the pin diagram for IC 74138. What is 74138? 3 to 8 decoder. IC 74138 is a 3 to 8 decoder. Okay. So with reference to this, you can say when this IC is enabled, this IC is enabled, then only it shows the decoder functionality. Okay. So it has 3 enable inputs. Okay, 3 enable inputs. What is the data on enable inputs required to make this IC is enabled? Okay, that is on signal line G1, the value should be 1. Okay, because it is active high, that is here the required value is 1. Whereas on enable inputs G2A and G2B, what is the value required to enable the IC? 0, 0. So for 1, 0, 0, the IC is in active mode. And it shows the decoder functionality. Okay, what is decoder functionality? For every input data on data inputs, for every combination, one of the output is in active. Okay, now for that action, let us draw a truth table. Okay, let us draw a truth table. Okay, so to make IC enable, what is the enable data? 100. Otherwise, the IC is inactive. It can't show decoder functionality. Right? Now let us draw truth table for this. Okay, it has certain inputs and outputs. The inputs are 3 enable inputs and 3 data inputs. Okay, so the enable inputs are G1, G2A, G2B. G2A, G2B are active low. That's why I am using extension L. Okay. Then data inputs are 3 ABC. A is the LSB bit, C is the MSB bit. ABC. A is the LSB, C is the MSB. Okay. Then 8 outputs. It has 8 outputs, all at the active low. That's why Y0, L, Y1, L, Y2, L, Y3, L, Y4, L, Y5, L, Y6, L, and Y7, L. Okay. Now, so for which enable input combination, it shows the decoder functionality for 100 combination. Okay. In other case, the IC totally inactive. All outputs at the inactive. Okay. So let us see first of all. Suppose if G1 is 0. If G1 is 0, whatever other inputs, if the enable input G1 is 0. Actually, the required enable data for making IC enable is 1. Okay, suppose if it is 0, whatever other inputs, other enable inputs and other data inputs, okay, none of the output is in active because totally IC is in inactive. Okay, since all are active low, you have to represent the value 1. Okay, suppose if G2A is 0, no sorry, G2A is 1, G2A is 1. Actually, to make the IC active mode, what is G2A value? Compulsory 0. Okay, but suppose if it is 1, whatever the other enable and data inputs, again the IC is inactive, hence all outputs at the logic 1. Okay, so similarly with reference to G2B, if it is 1, also the IC is inactive, hence all outputs at the logic 1. Okay, so whenever G1 is 0, G2A is, sorry, G1 is 1, G2A is 0, G2B is 0, the IC now is in enable mode. Okay, now based on the input data combination or based on the combination on the data inputs, okay, that is 0 0 now. For 0 0 0, so Y0 is in active, Y0 is in active. Since Y0 is in at active low, here you have to show the value 0, whereas other outputs are inactive, that's why with 1 we are representing, right? Similarly, under same enable input, under same enable combination, suppose if the at the data inputs the value is 0 0 1, 0 0 1, with reference to this, Y1 is in active, Y1 is in active. Okay, active means you have to show value 0, inactive means you have to write value 1. Okay, similarly other combination corresponding outputs also you can fill like this. Okay, for 1 1, Y7 is in active. Okay, this is the truth table for 328 decoder or IC 74138, 74138, right? Now with reference to decoder action, write the Boolean equation for each and every output, in terms of data inputs and enable inputs also you can write. Okay, so then realize the logic diagram. So this is a logic diagram. It needs 8 NAND gates, and you know each and every data inputs has to be represented both in true form and complement forms. These are the true lines and these are the complement lines and these are the true lines for A, B, C. Okay, and this is the enable input. Okay, so single enable input we represented. Okay, so before that actually it has three enable inputs. Okay, so G1, G2A underscore L, G2B underscore L. Okay, so this this is the enable input with reference to three enable inputs. Okay, so like that you have to draw logic diagram. Okay, similar fashion, in what way we developed in case of 2 to 4 case, the same way, no need to by heart this diagram. Also simply use one enable and the rest is same. Okay, suppose if you take Y0, Y0 is in active when A is 0, B is 0, C is 0. So the equation is A bar, B bar, C bar. So A bar line, B bar input, C bar input are connected as a data inputs to this NAND gate. Okay, and fourth one is enable input. Enable input how can you get? Through this structure. One is G1, another one is G2A underscore L, another one is G2B underscore L, right? So this is the logic diagram for this. Now see how to write VHDL program for this 3 to 8 decoder. Okay, let us start. First of all, you have to use the word library IEEE. Okay, library IEEE, because using your library and use clauses, you can get the explicit visibility, right? So library IEEE, then use IEEE dot standard logic 1164 dot all. Okay, these two are compulsory. You have to write. This is the standard library and this is the standard package you have to use before writing every program. Okay, after that, entity declaration. Entity declaration start with the word entity. Now we are going to write a program for IC74138, that is 3 to 8 decoder. So here I have given the name V74 into 138 is whatever the name you can choose. Okay, but but you have to follow the rules. Okay, the name should start with the alphabetic letter. Okay, not with the numeric. Okay, right? Then port uh, in the port, what we are going to write inputs and outputs. Okay, first of all I am showing enable inputs G1 G2A underscore L G2B underscore L, right? Means A1 is in active high, underscore L represents the active low. Okay, their mode is in, data type is standard logic. Okay, then coming to data inputs, it has 3 data inputs, but instead of declaring 3 objects, I am declaring only one object with the name A, but the object is in the vector notation. Vector notation means that object is created as an array consisting 3 locations, right? In standard logic, vector in is the direction or mode, input means input of data type is standard logic. It has 3 locations, 2 down to 0. That means A2, A of 2, A of 1, A of 0. Okay. Then with reference to output, actually we have 8 outputs. I am representing, instead of 8 object declarations, so I am declaring only one object, that is y underscore L, but it is declared in the form of array consisting 8 locations. Like standard logic vector 0 to 7. Okay, then end entity name. Very clear? This is the entity declaration for 3 to 8 decoder. Okay, let us see once. With the start with the word entity, the name of the entity is, then port. In the port, all inputs and outputs are represented. Enable inputs I declared separately, whereas data input in the form of array I declared. Similarly, output also I declared in the form of array consisting 8 locations, right? Then let us see how to write architecture body. Architecture body starts with the word architecture. Same name I am using for the architecture, but with the extension underscore A. Okay, that means architecture for the 74138 of name of the entity is. Okay, next one, internal signal declaration I declared here. Internal signal means signal declaration. How can you get this? How can you declare a signal object with the word signal name, that is YLI colon, data type is standard logic vector. It is also of size 8 locations. That is, this internal signal object also declared in the form of array consisting 8 locations 0 to 7. Okay, next begin, architecture begin. Okay, so after begin, the statement part starts. In architecture we have 2 parts, declarative part. Before begin, the part is referred as the declarative part, and after begin, the area is called the statement area. Here I am using with the select statement. Okay, with the select statement, it is a selected signal assignment statement. It's as per the syntax, that is with A. that is with the data input observation. With the data input observation, I am assigning some value to the output. Okay, that is with A, select Y, target signal line is YLI. Target is YLI. First of all, I am assigning the data to the internal signal. After that, I pass that data to the actual output, right? First of all, YLI is the internal signal. For this, I am assigning the data is 0, 1, 1, 1, 1, 1 when all zeros. Okay, when A consists 0, 0, 0 with reference to 0, 0, 0, which output has to be active? Y0, right? Y0. So that's why this is the Y0 position. This is the Y0, Y1, Y2 like that, because we declared it as 0 to 7, 0 to 7. So this is the Y0 bit, this is Y1, Y2, this is Y7, right? So in the Y0 position, I am using 0, whereas others are 1 ones. Okay, as per truth table, this has to be, right? Next, suppose if the A value is 0, 0, 1, the A value is 0, 0, 1, what is the expected data in the YLI? Yes, that is 1, 0, 1, 1, 1, 1, 1 like that. Okay, so this is the data when A value is 0, 0, 1. Okay, suppose if the A value is like this, it assigns this data to YLI. Okay, so like that, with reference to A value, you need to assign one of the binary value to the internal signal. Okay, then when others, if A value is none of these value, so Y0 at the YL is at all inactive mode. Okay, represented through value 1. Okay. This is the based on the data input, how output would be. Okay, how output would be, but that is represented first of all in the internal signal. Okay, now I am passing this internal value to the output based on the enable data. Okay, this is the based on the data input. Okay, so another input also there in IC, that is enable. Okay, so when the IC is enable, when G1 is 1, G2A is 0, G2B also 0, then only the IC is in active and corresponding input combination, one of the output is in active. Okay, so for that I am using conditional signal assignment statement, that is when else statement. Conditional signal assignment statement, when else. Its syntax is target signal, that is actual output YL. For YL I am passing internal signal data less than equal YLI. So one of the YLI value based on the data input is passed to YLI when condition, G1 is 1, G2A is 0, G2B is 0. Okay, that is G1 and not of G2A and not of G2B equal to 1. I am using an AND operation between these three enabled data. In case of AND gate or AND operation, it output equal to 1 when all of its inputs are 1, otherwise it is 0. Okay, so that's why I am using not of G2A, not of G2B. Okay, that is 1, 0, 0 means 1 and 1 and 1, that equal to 1. When this condition is satisfied, assign the internal signal value to this YL. Okay, else what? The signal is in, the IC is in inactive. That means all Y at the inactive. That's why the assigned value is all ones. Okay, so end architecture name. Okay, so the with else assigns a value to the internal signal based on the data input, whereas when else statement assigns the internal signal value to the output signal based on the enabled data. So like that you can write a VHDL program for a decoder. Right? So this is about the decoder and its pin diagram, IC's pin diagrams and internal logic diagram and VHDL program for 3 to 8 decoder. Okay, so in the next class you can see encoder. right?